All right. Okay, guys. Now what I'm going to do is demonstrate for you electromagnetic induction, which is Faraday's law. Faraday's law. And to do this, what I have is a simple ball magnet. You see the north and south pole labeled for this simple ball magnet. And I have this system here that has coils of wire going to this galvanometer. Now, what I want you to see is that there's no battery source here. The coils of wire are going to this galvanometer, but you notice if I turn to the back, there's no battery source at all here. No battery source. Okay, so I'm going to put this back down again. And now I'm going to take my ball magnet, and I'm going to use this north pole of this magnet here. Now watch what I do as I put the magnet in and out of the coil wire. Now, the deflection of this galvanometer means that there's current flowing. When this galvanometer measures current flow. So when it deflects to the left or to the right, it means there's current flowing. So what I'm doing, guys, I'm causing current to flow in a system that does not have a battery source. Okay? Now what I'm doing, I'm causing a voltage to be induced into the coil of wire. And as that voltage is being induced into the coil wire, and this circuit here is a closed circuit, in a closed circuit, if you have an induced voltage, you get current flow. And the greater the voltage, the greater the amount of current flow that you will observe. So again, I'm getting current flowing in a coil wire, and there's no battery source. This is called electromagnetic induction. Electromagnetic induction. Now, watch what happens when I go into a different coil wire. Notice the length of the wire. Notice the number of turns in a coil. Now I'm going to go from this number of turns to less turns. And notice the deflection of this needle. And then to a smaller number of turns in the wire. Notice again the deflection of this needle. Notice that we get more of a deflection with more turns in a coil. Okay? This is a large number of turns, smaller number of turns, even smaller number of turns in a coil. Now also, I want you to note the speed at which I go in and out of the coils will also determine the amount of deflection we get. If I go real slowly in and out, notice I get very little deflection. Again, real slowly, very little deflection. If I go faster through the coil wire, I get a much greater deflection. Okay? And if I turn from the north pole to the south pole, I still get a deflection, but notice how it's going to deflect down to the opposite side. Again, this is the south pole of the magnet going into the coil wire. And notice that the deflection is to the left. If I turn it to the north pole, you notice that the deflection is now starting to the right. But now, a very important point about what I'm doing, again, this is Faraday's law, and it showed you that given once, let's take this large coil here, this large coil arrangement, notice that again, that the speed at which I go in and out will determine how much deflection we have. So the greater the speed, the greater the voltage induced. And also notice that this is a function of the number of coils I'm using. Notice that the larger the number of turns in a coil, the larger the number of turns in a coil, also the greater the voltage. And the greater the voltage, the greater the current flow. So what we found here is that the induced voltage, this is Faraday's law, the induced voltage is a function of the number of turns in the coil and the rate at which the magnet is going in and out of the coil. That's Faraday's law.